All right, so if you remember back to the short period mode, this was a longitudinal mode. And we talked about how since this oscillates so quickly that the velocity doesn't have much chance to change. And we saw that when we did the simulation in the velocity plot, you didn't see that short period happening very quickly. All we saw was the long period, the Phugoid. So we can make an approximation that U is approximately constant, which means that the perturbation, which is a function of time, this is the constant forward speed, that this is small. And so we'll set it to 0. So we have, in the longitudinal mode, we have a U dot equation, a W dot equation, and a Q dot equation. And since the only unknowns we have are W and Q, which is theta dot, we can get rid of this equation and just use these two equations for two unknowns. So makes things a lot easier. So what we'll do is go back to the equations of motion and just grab those two equations. And yeah, I want page 109. So we're talking about these sets of equations here. Those are the force equations. There's the delta U dot equation, the W dot equation, and then we have the Q dot equation down here. So those are the longitudinal equations. The other three are the lateral directional. And so we're going to knock this one out. We don't need the U dot. We just need the W dot and the Q dot. And these deltas, the delta Z and the delta M, are the force and moment models that we developed along the way. We did the steady state part and the linear part, or the steady state part and the small perturbation part. So all we have to do is plug in for the Z force, which is really the lift. So that's going to be in terms of the angle of attack, which is W, and then the pitch rate and the elevator. And the same thing here. So we get two easier equations that come from that. So here's the full force equation in terms of small perturbations. And these Z things are those collection of variables that are in the table that I pointed to in the book. So this is fundamentally the lift. This is the lag in the downwash. Remember we talked about an alpha dot or a W dot term. This is the lift due to a pitch rate. If the tail's moving down, you get an induced angle of attack. And then this is the lift due to the elevator. And already we can start knocking stuff out because we said, well, this is 0. So we knock that out. The equation has this over the mass. And then we get And again, that's just copying the equation from the page where we derived it. And so now we just have two unknowns. And remember, Q and delta theta are connected together. So the input is elevator, and the outputs are W, which is angle of attack, proportional, and then Q, or theta. And then the pitch rate equation, the other degree of freedom, and so this is the pitching moment equation. Again, we're going to say this is 0, so knock that out. This is essentially contained in here is Cm alpha, because alpha is proportional to W. There's W dot, pitch rate, and the elevator. And then the relationship between delta theta and Q, so we can actually plug in up here and get delta theta double dot and delta theta. So we're going to get everything in terms of W and delta theta. So those are our two unknowns, and here's the two equations. So just like with the full 3x3 or 4x4, or the masses and springs and dampers, the process is we Laplace, because we're solving two differential equations. We Laplace and then solve and then find the roots of the characteristic polynomial. That's just the thing on the denominator. So the process is the same. Don't be confused by the fact that the aerodynamics introduces a whole bunch of stuff that we didn't have in the mass equations. It's still a dynamic differential equation. You Laplace it, you solve for the unknowns. All right, so let's put in delta theta, and then we're going to do the Laplace. So it's easier. We'll just do that on this screen. So this is going to become delta theta double dot. And so when we Laplace that, we're going to get s squared because it's a double derivative. And for Q, we're going to put in delta theta like that. And so that's in terms of W and Q. And then, of course, elevator is the input. It's like the force that we apply to the mass. So for another set of equations, you're going to do this process in the homework. So we're going to practice that today. So I want you guys to take this equation and Laplace it on your paper. Again, it's not hard. Use zero initial conditions. So I'm going to leave that up on the screen, but we're going to Laplace with zero initial conditions, because all we care about is finding the roots. And so it doesn't matter where we start out. We want to know what the dynamics are. So I'll give you guys a couple minutes, Laplace this equation. I'll get you started out. This is going to be S times W of S, right? Because it's first derivative. Put the M under each of the Z's to separate out these terms. Just Laplace each of them. Again, if there's no derivative, it just becomes like W of S. So take a minute. I'm having you do this so that you practice doing it with these equations, and then I'll give you the equations you're going to do for the homework. And then we'll check it. While you're working on that, I see a question in the quiz, or in the chat. There is no quiz this week. You're turning in the homework on Friday. No quiz. Unless I get emails from everybody in the class saying, oh, we want a quiz. Yeah, it's a joke. An easy quiz. All right, so hopefully you're mostly done. So let's do this. You get S times W of S. I'm going to put all the unknowns on the left side. I know I didn't ask you to do that, but that's okay. We're just going to rearrange so that we can put it into a matrix. So I'm going to shove all of the unknowns on the left and then keep the input on the right. So let's look at this term. We got a ZW over M. Those are just constants, and then that just becomes W of S. And then we got a ZW dot. That's a number. And then we get S with the derivative. No derivative here, so we just get delta theta of S. We're going to leave the delta E over on the right-hand side, but we get a plus G sine theta 0. And then this is our time function, so we get a delta theta of S. Oh, I forgot to make this. This is delta theta dot here. Credit, I forgot that here. This should have been dot here too. I botched you all up, right? That was Q, so it should have been delta theta dot. So we need an S there. We need an S here. So correct that in your notes if I got you off on the wrong track, because Q is delta theta dot. Then that's going to be equal to Z delta E over M. And then there's our force input delta E of S. So let's make sure I haven't messed something else up here. Looks good. And this one, same story. Laplace it, you get S squared minus mu over IY. Oh, that one's knocked out. MW. Got a derivative there that I remembered to put in now. And then that's going to be equal to M delta E over YY delta E. And I rearranged it so that now it's easy to put into a matrix. Here's our unknowns. So we just need to make sure that we put the right unknowns in the right spots in the matrix. So I'll give you a minute to work on that. Then we're going to write the matrix down. So we're going to get 3 W terms here and 3 delta theta terms, 2 delta theta terms, and 2 W terms in the second equation in the matrix. So this is step 1 that you're going to do with another set of equations that I'm going to give you here in a minute. Step 1 is to Laplace. And again, we do 0 initial conditions. Then we're going to put it into a matrix form. Give you a minute to get caught up here. All right, so then here's what the matrix looks like. So that's the first equation, then here's the second one. And so this is what you need for the homework. What you're going to do is you're going to substitute the numbers for all of the m's and z's. This is on page 6.2, oh sorry, table 6.2, page 166. And you're going to use the metric values. So everywhere there's an m or a z, you're just going to pull the number. The mass is in there. I think you have to flip back to the beginning, to the previous page to get the mass. So on page 165. But you're going to stick all the numbers in here. You got to use 0, theta 0, that's all in there. So these are just numbers. You're going to get s's times a number, s times a number, and a number here, s squared, s times a number. And then you're going to take the determinant and find the roots of the polynomial that you get. There is one typo in the table. The book has 10 to the 4th. It's 10 to the 5th. So make sure you notice this. Pardon? Yeah, it shows 10 to the 4th and it should be 10 to the 5th. So use this number here. No. I've worked this all the way up to here. Yeah, so you're going to start here, plug in the numbers, and take the determinant. And the next set of equations, I'm going to have you go through these steps, but there's less terms in it, so it's easier.
The first orbital of the matrix, dw over n doesn't have an s.
What did I do wrong? Oh, because it's not W dot, is it? Let me make sure. Oh. You're right, the parentheses should be like that. That's what you're saying, right? Yeah, it's because there's an S, because this was W dot, and then this was W dot of S here. You're right. So sorry about that. Thanks for catching that. So I did the hard work on here. You're just plugging in numbers and calculating the determinant and the roots. And so this is the short period approximation. And the nice thing about this is you can just hand calculate it. You don't have to use a computer to calculate the eigenvalues of that big matrix. And also, you can see once you calculate the roots, if you did it in terms of formulas, you could see how the roots depend upon various design parameters. Like MQ, this has CMQ in it, and MW, this has CM alpha in it. And so you can see how the roots depend upon the various stability parameters of the airplane. We don't have time to go through all of that in this class. If you run through it with the formulas here, you can see exactly how the roots depend upon those. And what that means is if the roots don't work out great, then you know what you need to change in the airplane. If we need more stability in CM alpha, we know we need a bigger horizontal tail to fix that up. So that's actually problem number 4 on the assignment. And then problems 1 through 3 are doing this process for an easier set of equations, which are the Fugoid approximation. So let me give you those, get you started on that. Again, it's simpler because there's less terms than what we just did. So that's why I did the hard one. So for the Fugoid mode, we notice that for the Fugoid mode, alpha doesn't really participate in that mode, that alpha is pretty much constant. So delta alpha is approximately 0, and that's proportional to W, the small perturbation W. Again, remember W is 0 and the stability axis is 0, so W is the perturbation. And it turns out people have experimented, well, which 2 equations do you keep with this? It turns out that if you keep the lift and the drag equation, so this is the delta U dot equation, and this is kind of counterintuitive because W dot is going to be 0 because we're saying W is 0. But it turns out if you, backwards. The lift equation is the W dot equation. This is the delta U dot equation. So we keep this equation, we're actually going to knock out the W dot, which makes it easy. So this equation, the drag equation, looks like this. And again, I'm grabbing those from that page in the handout or in the book. So we're grabbing the delta U dot equation again and the W dot equation. The W dot was yeah, we're grabbing those 2 equations, not the pitching moment equation like we did last time. And we're plugging in delta Z and delta X, but now we're going to knock out W. And there's a lot of W terms in there, so those go away, and that's what makes this easier. Let me unshare the screen. So the delta U dot equation which is the one we threw away earlier. Looks like that, where we plugged in the drag force model. And here we're saying W is 0, so we knock that term out. So you can see this is easier. It's just got one term here. And so we'll Laplace that one, and then the W dot equation. Again, counterintuitively, we're going to knock out the W dot because we're saying W is 0. But it turns out this gives a good approximation. And so W is knocked out, so that goes away. That goes away. We're saying those are small, and this is 0. So you can see that simplifies down quite a bit. So make sure before you Laplace, so step 1 is going to be Laplace, but I guess step 0 is to plug in, everywhere you see Q, plug in delta theta dot. And the homework walks you through this. So you plug that in, you Laplace, you put it into the matrix, and then you find the determinant. And the determinant's going to be easier because there's less terms. And you stop there. I'm not going to, do not plug in any numbers in this one. You just stop at that point. But I want to give you practice in how you do that. So step 4 is to stop. All right, any questions about the process or what you're doing for the homework? Yeah. Uh-huh. When you put it in the formula that we didn't put it in, let me back up. So we did not put it in state space form. So then you just take the determinant and find the roots. And the reason for that is, again, it's just Kramer's rule, right? We have this in the form of a matrix times a vector equals a vector, and this is our Laplace variables. So we don't have it in the form of dots equal AX plus BU, right? We just have it in terms of a matrix. And so if you solve this, our first unknown was W, right? So if you solve for W, remember what you do is you have in the numerator the determinant of this matrix with the first column replaced by this. And in the denominator, you just have the determinant of the matrix. And that's where you get your roots for the partial fraction expansion. So you're just finding the determinant of that matrix. Whereas if it's in state space form, maybe this is too long of an answer, I hope not. It's in a different form. That's already Laplaced and both sides put on the other side. And over on, if you Laplace this and put it in this form, you get S I minus A times X. And so that's why this is the eigenvalues of A, which are the same thing as the roots you'd get. Essentially, when you put it in state space form, you solve to get that formula along the way. But these are the eigenvalues of A, but the eigenvalues of this thing are not the same as what you get over here. Sorry. Yeah. Good question, though, because if you put it in state space form, then you don't even have to get it into this form. You just find the eigenvalues of A. So I could have had you put these in state space form, but typically you just go through this process. Next, I want to show you how I graded the homework. I'm sorry, graded the quiz so that you can check that. This is the quiz you got back last time. So the last thing we'll talk about for the semester is once you get the roots and we look at them, we see that it has a real part. If the real part is negative, which screen am I on? Over here? Okay, good. So we get a set of roots. You look at the real part and you say if it's negative, it's stable. And if it has an imaginary part, then it's oscillatory. Right, but we'd like to go beyond that. Is it stable enough? Is it too fast in oscillation if it's oscillatory? And so that requires a little bit more of what's called a mode analysis. Which means we look at the roots and we look at the real part and the imaginary part and say, well, that looks like it's stable enough. And it looks like it's oscillatory and it's good. Some roots, remember, just have, they don't have a real and imaginary part, they just have a real part. And so we'll look at how you analyze those first, and then if you get complex conjugate pairs, we'll talk about how you analyze those. So we probably have time to look at just the first order mode, the real part, and then we'll do the rest next time. So, am I on the screen now? Yes, I am, okay. So if we have a real root, then it's called a first order system. Because it comes from a first order polynomial term. When we do the partial fraction expansion, we keep it as 1 over s plus some number or minus some number. Remember, if we have complex conjugate roots, we don't split it up into the two plus and minuses. We keep it all together as s squared plus s plus a constant. So if it's a real root, no imaginary part, we look at it like this. This is the partial fraction expansion. And I just put a 1 up here. You know, there may be some other constant that goes along with it. Those are the K1 and K2s that we find. But when we inverse Laplace it, we get e to the at. This a goes up here, and we hope that that's negative so that we get e to the minus a number times t, and it damps out. So we want a to be less than 0 so that it's stable. And this is usually analyzed in terms of a time constant, where the time constant is defined to be minus 1 over that root. So we just define that. We say, well, this is minus 1 over tau because we just substitute in for a here. But the reason that people talk about this is when time is exactly equal to that time constant, then if we plug in for t, we get e to the minus 1 over tau, and then time is at that value, we get e to the minus 1, which is 0.368. And really that's saying, well, that's the time to damp to that value. So at t equals 0, this term is 1, right? E to the 0 is 1. So this term starts out at 1. And then if it's negative, it damps down like that. And when it gets down to that 0.368, that's what we call the time constant. So it's just a measure of how fast it damps. We could talk about A, but especially this comes from electrical engineers talking about electrical systems. They like to talk about the time to damp to 1 over E. And it's just a standard. That's how you talk about your system. You would say, oh, my airplane, the roll mode has a time constant of 2 seconds. And everybody goes, oh, okay, that's good. So again, we're going beyond whether it's stable. And so the bigger tau is, the smaller A is, and the longer it takes to damp. So your time constant can be too big, which means if a gust comes along, the airplane responds and it's well damped, but it takes a long time to return back to steady state cruise flight. Just like with the mass spring damper system, if we pull it over and it has a high time constant, we let go, it takes a long time for it to come back to equilibrium. How are we doing on time? Let's see, we'll get into some actual numbers for the BizJet next time. We'll do that.